Covalent bonding, part 4, assigning delta plus and delta minus dipoles when we have polar covalent bonding. In this video, we're going to be talking about electronegativity. Now, if you haven't seen the last video about predicting bond type using electronegativity difference, you should watch that last video before you watch this video. But just a quick review. Electronegativity is a calculated value, and it can be looked up on this reference sheet, or some other reference might do too, where there are electronegativity values present. Here we can see the electronegativity values are written in the box by each element symbol. So for example, the electronegativity for S, sulfur, is 2.5. The electronegativity for Be, beryllium, is 1.5. Remember, electronegativity generally gets bigger as we go up and to the right. Electronegativity is a calculated value. It's not directly observed, and luckily it's been calculated for all these elements for us. The low end of the electronegativity scale is 0 and the high end is 4. The element with the biggest electronegativity is fluorine, 4.0, and the element with the smallest electronegativity is Fr, francium, 0.7. Electronegativity is defined as the attraction that an atom has for bonding electrons. That would be any valence electrons that get involved in bonding. The valence electrons from the atom itself, and then from any other atom as well that would be involved in the bond. So it's all the bonding electrons, all the valence electrons involved in bonding. Now, what we can do to predict bond type, one way we can do it quantitatively, is to look up electronegativity values for elements. We subtract the larger electronegativity value minus the smaller electronegativity value for two elements in a bond. If the difference, and you get a difference by subtracting, is greater than 1.67, then we say that the bond between those two elements is ionic. If the difference is greater than 0 and up to 1.67, anywhere within that range, we would say the bond is polar covalent. This is where we have unequal sharing of electrons. And to signify that one end of the bond is slightly positive, we put a delta plus there. And to signify that the other end of the bond is slightly negative, we put a delta minus there. These are called dipoles. They always come in pairs, dipoles. So one end of the bond in a polar covalent bond will always be delta plus, a little bit positive, and the other end will always be delta minus, a little bit negative. If the electronegativity difference between two elements is 0, that is to say the two elements have the same electronegativity value, then we have nonpolar covalent bonding, and that means equal sharing of electrons, so no uneven distribution of electrons, right? It's an even distribution of electrons, and there are no dipoles. So, dealing with bond polarity is something that we really only have to pay attention to when we have polar covalent bonding. Polar covalent bonding has delta plus and delta minus dipoles. Nonpolar covalent bonding does not. We can say that the more electronegative element in the bond would be labeled delta minus. And again, this kind of a rounded off D with a little squiggle at the top is Greek letter delta. It's a lowercase delta, just about where the D is in the Greek alphabet. The less electronegative element in a bond would get the delta plus charge. All right, let's take a look at some examples. If we look at CH4, the chemical formula, we can see that C is going to be bonding to H. C has an electronegativity of 2.5, and H has an electronegativity of 2.1. So, let's write those down, and let's subtract the larger minus the smaller electronegativity values. The difference is 0.4. Now that's greater than 0 and less than 1.67. That means that this is polar covalent bonding, and we need to assign delta plus and delta minus dipoles to the atoms in the molecule. So you have the structural formula here, the two-dimensional structural formula, or also known as the Lewis structure. And what we do is, for the larger electronegativity value, that would be for carbon, we put a delta minus somewhere in the vicinity of that element. It doesn't have to be in the upper right. It could be on the left, on the top, or the bottom, but somewhere around that element. And then the element with the smaller electronegativity, in this case hydrogen, gets the delta plus. Now once again, delta minus signifies a slight negative charge, and delta plus signifies a slight positive charge. Now, we don't write 4 delta minuses around the carbon. It's understood that for each one of the bonds, the carbon is the delta minus and the hydrogen is the delta plus, by just putting 1 delta minus by the carbon. Let's take a look at an example where we have nonpolar covalent bonding. Here's one, NCl3. Notice that the electronegativity of N is 3.0, and the electronegativity of Cl is also 3.0. So 3.0 minus 3.0 gives a value or a difference of 0, and 0 electronegativity difference means that we have nonpolar bonds. So that means we assign no delta charges, no delta pluses or delta minuses at all on that kind of a molecule. A couple more examples. Here we have CO2 carbon dioxide. You might be familiar with that. Carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. So let's write those down. We always subtract the big electronegativity minus the small electronegativity, and when we do that, we get a difference of 1.0. Now remember that an electronegativity difference that's bigger than 0 and less than 1.67 indicates polar covalent bonding. When we have polar covalent bonding, we assign delta plus and delta minus charges to the atoms. The larger atom, or rather the atom with the larger electronegativity, always gets the delta negative. So the oxygens both get delta negative. And it can be somewhere in the vicinity of the symbol. It can be on the top or the bottom or anywhere, but it should be somewhere around each one of those oxygens. And the smaller electronegativity, or the element with the smaller electronegativity, gets the delta plus. It's that simple. It's always going to be that way. The element with the larger electronegativity gets a delta minus. The element with the smaller electronegativity gets the delta plus. Here's our last example, Si2H4. The electronegativity of Si is 1.8, and the electronegativity of H is 2.1. So let's write those down. Now each bond has an Si and an H in it. So we don't have to worry about exactly how many Si's and how many H's there are. We just look at each individual bond. So we compare Si to H directly. So 2.1 minus 1.8, remember we always subtract the bigger minus the smaller electronegativities, will give us a difference of 0.3 for an electronegativity difference. Well, that means it's polar covalent. It's greater than 0 and less than 1.67. So now we look at those electronegativity values. The element with the larger electronegativity gets the delta minus. So we put delta minuses by each one of the hydrogens. And the element with the smaller electronegativity, silicon, has 1.8 electronegativity, gets the delta plus. So we put delta plus by each one of the silicons. And since we're comparing each bond directly, that's all we have to worry about. Now you might say, well, what about the silicon-silicon bond? Well, there would be equal sharing of electrons across that bond, but the silicons would still be slightly positive because they would not be sharing electrons equally with the hydrogens. All right, so if you understood what we're doing, then you should be able to do this. Copy these 5 two-dimensional structural formulas, also known as Lewis structures, and assign delta plus and delta minus dipoles to the atoms in these structures. These are all polar covalent bonding, so they will all have delta plus and delta minus dipoles. Good luck.